Why do we want to round n up? To make sure we don't exceed a margin of error, a particular given margin of error. What do we know about n? The higher n is, what happens to your confidence interval? The width decreases. So by rounding n up, always, we'll have a slightly lower width, which means a slightly lower error. Or we're not going to get it, we're not going to exceed. If we round n down, we're going to exceed, we're going to have a wider interval, hence a wider error, and exceed that particular value. So we always need to make sure that we are rounding n up to the next whole number, and that's because we are, unless it says round to the nearest, that's because we don't want to exceed a particular margin of error. And there is often a mark for that rounding. Now with this one that we did, it's only natural that you would think, oh, 153.69, well, that'll go to 154. But if I was writing a question, it would be 153.2, and you'd have to round up to 154. You know what I mean? Like, I try and get it where it forces you to round up, which is not your natural instinct in terms of how you would round. So that is that one. Now, the next example, I'll leave you to do for homework. That is just pretty standard, and the solutions are here. So you've got them all there. It's actually quite a good one in terms of, comparing what the true proportion is to a sample and thinking that someone's been ripped off. But I want to get into the next thing, which is a little bit more thought about the margin of error. So capital E or lowercase e doesn't matter. I think I've used capital E, but your E activity uses lowercase e. Some books use lowercase e. I want you to think about this scenario. And that is, when will that margin of error be the greatest? Given your sample size is a fixed number, whatever that is, your Z is a fixed number, but what does your sample proportion have to be such that that margin of error will be the greatest? I want you to think about that. So when we multiply P by 1 take P, just that part of the formula, I guess, the highest number that you can get is based on P being 0.5. And we can see that graphically very quickly because that's a quadratic. Your roots are 0 and 1. It is a quadratic with a maximum turning point, and the maximum occurs at 0.5. So that's why. And you could actually prove that using calculus if you wanted to. We could actually differentiate and find the maximum for a fixed, with where Z and N is fixed. But just to look at that logically, that part of the equation, regardless of whether you divide by n square root and times by Z, this is the key. That bit's the key. And the maximum will always be when P equals 0.5. So the moral to that story is, if you do not have a sample proportion, then in a problem, and you want to make sure that you've got that maximum margin of error, well, you have to ensure you cater for the maximum margin of error is probably more the point. We've got to use P hat is 0.5. So if you don't know, you use 0.5. And that'll ensure you've got your maximum margin of error. So that applies in questions coming up. I guess I've already answered that. So in the first example, we do have a P hat value. It is thought that about 60% of Year 12s obtain their driver's license before they finish. How large a sample would be needed to estimate this within a margin of error of 5% at the 90% confidence level? So what is it that we need? We know the error. We know the Z-score. What is the Z-score at the 90% level? 1.645. Very good. N is what we're trying to determine, and P or p hat, it's thought, that should end in a t, about 60%. So that's your p or p hat value. Now, yesterday we rearranged that margin of error formula to look like this, if you remember. You could use the E activity to put in your numbers, or you can substitute straight into there. The best thing about the E activity is that it keeps everything as exact as possible, because the first thing you would do is find your Z-score at a 90% confidence level. And then that Z-score then stays in the calculator when you go and find your sample N, because there could be variation in it, which is fine as long as you show all your working. Z-score we don't want to change. Margin of error is 0.05, and we solve for N. So I'm getting 259.73. So we want to have that margin of error of 5%. So we need to ensure that we round that figure up. So that goes up to 260. Now, if you did not use the E activity and you use 1.645, you probably won't get 259.73, but you'll get something around about that figure. So just be wary of what you're using and just show your working. That's important. All right, so the question is, what if you have no information about P? Well, I answered that P hat. I answered that before. We've got to use the one that produces the highest margin of error. So we've got to then ensure, and that's that whole point then of ensuring that you've got that interval width that's wide enough. So I'll let you read that question. Same question, except we don't know the proportion. Still at the same level of confidence. N is the one we don't know, and then we make the assumption that P is 0.5 or P hat. Yep.
Where they say, how do we know we just assume P hat to 2.5?
Yes, because you don't have any other information.
Oh, so we just assume.
So you have to make that assumption. Yep. So I've already got my Z-score established in my E activity. So according to the E activity, 270.55. But this time I wrote the working out manually, so you can see what I mean. Just put your Z-score in, your P hat and your one take P hat, obviously. And so then we say N equals 271. Don't assume it has to be a nice number. Some of you did that in your investigation, which, by the way, I'll get you back tomorrow. So when we solve that first derivative equal to 0, we get P hat is a half. So there's your 0.5, and we saw that graphically anyway. And then I just said that the second derivative was, without actually working it out, but it is -2, and hence it's a negative, and therefore it's a maximum. All right, so in part B, using that idea, consulting firm wants to determine P within 8% with 99% confidence. How many time vehicles should be tested? We've got nothing about the sample proportion, and so we use 0.5. So when we don't know anything, we would use 0.5. Z value, Cindy, what is it for 99%? 2.576. And a margin of error of 0.8. So, and N equals whatever. So you can see this is a waste question, so they've thought about it a little bit better. because when we stick these numbers in, using the E activity, I'll go back to the Z score for CI. I'll try and get that exact confidence level 0.99 this time. And then sample N, margin of error is 0.08, sorry, solving for N. So 259.17 or 259.2 will do. So your natural instinct is to say 259, but if you do that, you will exceed the 8% error. And so we therefore need to round up. Yeah, that's what I was been saying.
So with sampling, just ignore the instant and just round.
Well, it depends on the question. If you try, so we round N up if we're trying to find the N value for a given margin of error, but the confidence level we have to round down if we're trying to find a given margin of error, right? So you've got to be careful. Now, I've never seen a waste question where they've asked you to get the level of confidence that I can think of. So at least that's a moot point. You don't have to worry too much. Remember rounding up. But ideally, yeah, the confidence level, we talked about that yesterday. We've got to round that down. But N, we round up to ensure you're within 8%. Because if you did this and wrote that in at 259, I'll show you. Let's put it in. If I put in 260 and I solve, I mean, it's very minimal, but even so, put 260 in, same parameters, but this time I'm solving for E. You can see, 260 works. You can see how 260 has a margin of error of slightly less than 0.08 or less than that 8%. But if I put in 259, that was what I was meant to do, and solve for E, you can see how 0.08 is exceeded, not by much, but it's still exceeded. And you want to be within that 8%. So that's outside of the 8%. Hence, we have to round up to 260. All right, we'll keep going. So in summary, using calculus, we differentiate and solve equal to 0 to find the maximum value. And in this case, we can prove that the maximum value for that proportion is a half. Using that half now in the next problem, we can solve for N. We have a margin of error of 8%, so we were trying to go within 8% of the proportion figure of 0.5. And in order for us to do that, it's got to be 259.2, we solve, and we've got to round up at 260. We round up because if we didn't, with our margin of error of 0.08, just to show you, if that N value was 159 and we solve for E, no, something's not right there. My proportion should be 0.5. If we solve for E, I must have the wrong Z value as well, do I? No, N is 59, proportion is 0.5. Solve for E, I'm looking at 259 here. Try again. Okay, and you can see how that 0.08 has been exceeded, and hence the reason why we've got to use 260 as our N value, and when we solve for E, it's slightly lower than 0.08. The next problem, easiest way to determine the margin of error is just to work out the interval width, the difference between the endpoints of the confidence interval, and halve that. You could use the method of finding the sample proportion first. And so remember, the sample proportion is in the middle of the interval. So there's your 0.342, there's your 0.558. So find P hat, and then the difference between the 0.558 and your 0.45 gives you your error. Either way, sticking those values into your E activity we get n is 140.8, which we would round to 141. At that point, we haven't answered the question. In order to answer the question, we need to know the number in the sample. The number out of 141, that would give a sample proportion of 0.45, and that number is 63. So just be wary of this, because it's asking for number, not proportion. That gives you a little bit of a hint in terms of whether we use binomial or not. And so number with binomial, n is 30. And then the probability that at least 27 chocolates are pink. And again, we're looking at a number of chocolates as opposed to a proportion. So straight into binomial and using the parameters of 30 and 0.8. And we want at least 27 means we include 27. And I'm getting 1.227. And because it said to 3 decimal places, you must give it to 3. So 0.123. All right, now we're starting to talk proportions and confidence intervals and so forth. Sample sizes of 20 boxes. So suddenly we've got 20 boxes. How many chocolates have we got? 7 chocolates?
I don't know.
600. Let's try that again.
I was close.
Why 600? Each box has 30 chocolates in it. So we've got 600 chocolates now in the sample. So each sample has 600 chocolates, and we want a 95% confidence interval for the proportion of pink chocolates in your sample of 20, and we're making the assumption that 80% are pink, so that's your proportion. N is 600. And if we are putting this in, how many of that is pink? Well, 80% of 600 is going to be 480. And your Z-score at the 95% level, we should know that now.
1.645.
No.
1.960.
1.96. All right, so doing that,
Close.
either E-activity or what have you, I'm getting these figures. So that's the easy part, that confidence interval. So you can use your CI for proportion. If you do, make sure you write those things down that I've written. So we want 480 out of 600. And the confidence level is 0.95. And you might want to write the standard deviation as well. Or the error. I don't know. It's better to have more. Depends how many marks. I mean, this is only 2 marks. This is only 2 marks, so you don't have to worry. But it's good to have some things down there.
What is that symbol?
That's meant to be E. Sorry.
It's just a little spider at the moment.
Yeah, because I was writing it as standard deviation. I thought, oh, well, standard deviation, but it is, now you know that it's error. It's the same difference. Okay, let's have a look at part D. I'll give you some time. So your 95% confidence interval, we're taking 3 samples. Our true proportion is that. We're taking 3 samples. That might be 1. That might be 2. And that might be the 3rd one. I don't know. Out of those 3 samples, what's the probability that only one, so that scenario that I've just shown you there, does not contain the true proportion? Well, what's the chances? What's the percentage that it's not going to contain the true proportion?
0.05.
Yeah, so 0.05 as a probability, 5% as a percentage. So it's going to contain the true proportion or it doesn't. What have we got in terms of our distribution? It's a binomial.
Okay.
So you can do it this way, probably easiest. So 5% chance, and we want 1. So setting up your binomial and 1, I'm getting this figure.
Oh, where does 3 come from?
Because it's 3 samples.
Oh.
So it collects, yeah, that 3 collects your 3 samples. So there's your 3 samples. What's the probability that one of them doesn't contain the true proportion?
So in May's questions, they'll have like a sampling question, and then they'll have like.
Well, you can see how we've gone from binomial to confidence intervals, back to binomial, different binomial, and now it's going to something else. So yeah, it does like to chop and change, as you can see. Using the 95% confidence interval that we found already, determine the range in which the expected number, so now we're back to number of chocolates. So the expected number would lie. So how would we do that? Logically, how would we do that? Yeah, so you've got your interval 0.768 and 0.8320. That's your two outer ends of the interval. So you would expect, if there are 600 in a box, we times that by 600. And this one. Now, there's another one where they actually accepted anything. However, I'm going to give you some technical thinking. 460.8, 499.2. They accepted 461, 499, 460, 499, 500. They accepted the variation. However, that was that year. That was a few years ago. I want you to think about how we can be sure that we have a 95% level of confidence. How can we be sure? How do we have to round to be sure? Yeah, up for the one on the outside, right, and down for the one on the other side. So yes, rounding out is what we use, that term. We need to round out. So you've got your 460.8 here and your 499.2. To ensure that level of confidence, we have to round out. So the actual correct answer should be, that goes out to 460 and this one goes out to 500. So sample 2 is okay, 3 and 4 are okay, 433 is too low, it's lower than 460, and 566 is too high. So samples 1 and 5 lie outside that range. Now, there's no further questions there. Oh, sorry, for the parts to this question, what I mean. So they lie outside the interval we gave. Now, if we were to look at this a little bit more, that's 2 out of 5, right? That's a pretty high proportion. So what might that tell you? Well, it might tell you that the proportion of pink chocolates, or the chocolates that they're suggesting are pink, might not be right, because they've suggested from the beginning 80% are pink. I don't know. I mean, the fact that one's lower and one's higher might negate that idea, but you would have thought that given, you know, what we've suggested, 3 out of 5, that's not much. But anyway, just a thought, just something to think about. Not that they've asked you to do anything with that.